An object is released from rest at an altitude h above the surface of the Earth. Show that its speed at a distance r from the Earth's center, where re, the radius of the Earth, is less than or equal to r, the quantity, which is less than or equal to re plus h, is this equation. So I'm going to do part A first. And it was not pretty. So what I did was I used the kinetic energy work energy theorem, and Mr. Greenberg showed us how to use this in class. So it's basically the kinetic energy, the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And I crossed out initial kinetic energy because there is no velocity initially. It's just space at zero at some point. But we do know that the potential energy is negative gmme over re plus h, and we remember if it's just like there's the height is some infinite distance away, and that's why. And this is the object right here. So, this is some infinite distance away, and that's why this is negative. And then we have kinetic energy with a final velocity squared, and we have another final potential energy. Now, the difference between these two was that the initial radius, the initial distance includes the radius of the Earth and the height. And then in between the time interval so right before basically this falls to RE, it's R because R is between RE plus H and RE. It's that final potential energy. When it reaches RE, there is no potential energy any longer, technically. Okay, so then we just isolate. Once we know that, the problem becomes more straightforward, and we just isolate V with some algebra, and we get the square root of 2 GME times 1 over R minus 1 over RE plus H, close parentheses. So that is exactly what we should be getting here. Okay, and then I screwed up a lot in part B, but I will show you how to do it nonetheless. So I had to flip the page over. So now it says, for part B, assume the release altitude is 500 kilometers. Perform the integral, and the integral is listed there, to find the time of fall as the object moves from the red release point to the Earth's surface. The negative sign appears because the object is moving opposite to the radial direction, so its speed is velocity equals negative dr dt. Perform the integral numerically. So now here's some useful quantities before you solve, just from my friend Google. The mass of the Earth is 5.972 times 10 to the 24th kilograms. The radius of the Earth is this value, and you have to convert that to meters. Don't forget to do that because that's extremely important, because G also, G's units are newtons times meters squared per kilogram squared. And same thing here with the height. You also have to convert it to meters and get 5 times 10 to the 5th meters. Okay, so now that we know that, we are going to find the integral. So we know that velocity is equal to negative dr dt. If we isolate dt, we're going to take the integral on both sides with some initial quantity in terms of height and some final quantity. And what we get is a negative outside, and the initial being radius of the Earth plus height, and the final being the radius of the Earth. And that makes sense, right? So, because it starts at the highest point and then falls all the way to the radius of the Earth, distance of the radius of the Earth. It doesn't fall the distance of the radius of the Earth, it falls some distance h, and that's why RE is the final. So then we use dr again and divide, and this time we found the velocity already. We know what the velocity quantity is, it's right there. So we just plug it in. And then this becomes, again, more straightforward because we only are looking for one variable, or just taking the integral of one, with respect to one variable, r. So once we know that, we just plug in our values, and it becomes quite a disgusting integral, but that's all right because we have calculators. And when you plug this into your calculator, you get 339.97, which is approximately 340 seconds, and that is the answer that you get.